Good morning, everyone. My name's Caitlyn, and I'm nearly a second-year PhD student now here at Monash, and I work with Daniel and Christoph, and I'm part of the EXO-ALMA collaboration, which is looking for baby protoplanets in protoplanetary disks with ALMA. And today I'm going to talk to you about the work that I've been doing over the past year, which has culminated in a controversial statement of no turbulence in the disk surrounding the star DM Tau. And also I'm going to be talking to you a little bit about obtaining more accurate protoplanetary disk parameters, as I've been developing a code that will hopefully do just that. So first of all, what drives mass accretion and angular momentum transport in disks? The answer is we don't know, unfortunately. So it's a bit of an open question in protoplanetary disk circles, but a potential solution is turbulence. So most protoplanetary disks have been measured to have turbulent velocities of about less than 5 to 10% of the sound speed within them. However, 3 years ago now, so in 2020, Kevin Flaherty and his collaborators released this paper that's found turbulent velocities in the DM Tau disk of between 25 to 33% of the local sound speed. So it's the first and only disk to have such high turbulence measured inside. So in their paper, they assumed a fixed stellar mass of 0.54 solar masses from the literature, and they fit for the following parameters. So the temperature scaling index, the critical radius of the disk, turbulent velocity, different temperatures in the disk, the inclination, inner radius, and the systemic velocity of the disk. And they found a turbulent velocity of about 60 to 80 meters per second. And here are some plots from the paper just to show you. So this is a line profile. So basically, you've all seen the channel maps that you can get from your data cubes. So basically what a line profile is you sum up all your flux in each individual channel, assign it to the corresponding velocity, and you get out this double-peaked Gaussian here. And so basically what Flaherty found was that if you didn't assume a turbulent velocity, you ended up with an underestimation of flux in the systemic channel of the disk. So when I first started my PhD, I didn't really know too much about disks, so I was having a bit of a play around with Phantom and MC Foss to figure out what was going on. And we realized that if you change the mass of the central star, you got something that looked like turbulent broadening in the disk. So as we can see here, we have a half a solar mass star in the center, 1 solar mass star, and a 2 solar mass star. And as you increase the mass of the star, your disk becomes smaller in the systemic channel. So here I have a plot showing different central masses for the star and the actual DM Tau disk from the EXO-ALMA data. So this was like one of the first lots of data that they put out. So we actually have higher quality data now than this. But even back then we were looking and we were like, this disk looks kind of big in comparison, looks kind of small in comparison, sorry. We reckon that based on like the amount of flaring that you get, even going to a lower mass still looks pretty good. And to confirm this, we ran a brute force model generation, changing only mass and turbulent velocities in the disk. And we found that there's a really big degeneracy down at the bottom where you can basically have any central stellar mass with a very low or no turbulent velocity at all in the disk. So we wanted to expand on this and figure out what was going on. So what I've been doing the past year has been to vary the following disk parameters in our models. So there's a lot of overlap with the Flaherty paper, so disk inclination, the stellar mass. We've also got the scale height, the flaring exponent of the disk, things like position angle, and the dust settling parameter, as well as the turbulent velocity. And so what I've been doing is we vary these parameters in MC Fost models, so use PyMC Fost to update the parafile for each model so you don't have to do it manually. Unfortunately, Phantom takes too long in the models, so we've had to kill it a little bit. So it'll come back one day, but for now I'm just using MC Fost. And once we have our different models, we compare it to the data and we form minimization on it. So I've been using a couple of different methods. So first we tried using SciPy Optimize, in particular a optimization method called Sugar, I think it's called. And then we've also used just MCMC It's like the MC package. So for my code, what we started off with was stage 1, which was just comparing the line profiles. So basically, steps are pretty simple. We would generate MC FOSS model with the velocity channels that corresponded to the exo-alma data. We would sum over the flux in each channel to obtain the line profile. We would subtract the values of the line profile that we got from the data ones, and then we would calculate a reduced chi-squared using the uncertainty, which we determined by I based on the line profiles that we were getting out. So it was about 2 Janskis per channel. However, there was a problem with this approach, and that's because we did lose a lot of information about the spatial dimension of the disk. So basically, when you are summing over the entire disk, you're just getting your one flux value out. It doesn't necessarily mean that it's a good fit because the flux could be located in different areas of the disk, or like your shape of your disk could be entirely different. So we had to move on to stage 2, which was looking at the image plane, which I currently am still working on. So when we hit image plane fitting, there was a bit of a snag because you have to fit each individual pixel in each individual channel. So basically your number of pixels to fit X by Y times your number of channels, which if we continued on in the same way we had for the line profile fits, would have been 43 million pixels, which is a lot. However, we decided to shrink down the size of the data cube as well as our model sizes, so that way they took less time to run. So we did that using Christoph's CasaCube tool. And then we also picked only 9 channels to look at this time, so it could reduce the number of computations. So we stuck with like the systemic velocity and then the peak, and then I picked a couple of extra ones so we would get the full extent of the disk. So in a similar way, we would generate an MC FOSS model with the 9 velocity channels which corresponded to the data, store every flux value per pixel, then we would subtract the individual pixel values from each other, and then calculate the reduced chi-squared. And I'm still having a bit of issues with how to calculate the uncertainty here. Currently, our chi-squared, they are quite low, but they're all quite similar, so I want to get a bit more variation in that. But it is still giving nice-ish results, but the uncertainties are just not trustworthy at the moment. We are currently looking at a new approach, but before we go into this, I have to take an extremely brief and very non-comprehensive interlude and talk about radio astronomy. I hope no one here is a radio astronomer, because I really don't know too much about it. But if you would like to learn more, I can highly recommend David Wilner's Amiga lectures on radio interferometry, because that is what I have been watching to try and learn more. So basically for telescopes like ALMA, because they need such high angular resolution to observe at small scales, you need to have a long baseline. So what we do is we have our multiple antenna. So basically for a 2-element interferometer like this, you get your radio waves coming from a particular source, but because they're separated, you obviously get like a little bit of a time delay in between the 2 signals. So what we're measuring here is they multiply and integrate the signals that they get, and you get a measure of something that's called the coherence, which is also known as the complex visibility. So it's not exactly the brightness that you get on the sky, like a nice 1-element telescope, but basically all we've got here is a 2D Fourier transform of the sky brightness distribution. So your complex visibility function is measured in terms of U and V, and they're your Earth-based coordinates. So they are talking about your telescope position on the ground, and your sky brightness is measured in terms of your L and M coordinates, which are your sky-based coordinates. And so basically, when you measure your visibility on the ground, you get some measurement of the sky brightness distribution, like at all L and M. It's a little bit confusing. I'm not fully 100% sure how it all works, but basically what happens is you have your configuration of antenna. Each baseline provides you with UV points, and as the Earth rotates, you end up with different sky coordinates as well. So basically you trace out these little tracks, and if you move all your antenna in closer, your UV points become smaller, so you get a more concentrated pattern in the center there. And basically the aim of the game is to try and get as many points in a UV plane as possible, so that way when the image calibrators perform their magic and they convolve this with some point spread function and suddenly it's an image, then they have more accurate functions for that. So I hope that that made some sense at all. Because stage 3 is visibility fitting, which is currently in development. So I was fortunate enough to talk with Sean Andrews last year. He has a code which is called CSALT, which stands for Circumstellar Spectral Analysis with Line Tomography. And it's a code that you can generate synthetic visibilities with. And you can also you can pass in models that you've generated with other codes and get the visibility distribution out of that. So what I've been doing most recently is a couple of steps in order to get CSALT working, because unfortunately it's still very much in development and not documented. So I've been trying to figure out how it even works. So basically what happens is you get the raw measurement set or MS file. That's what you get from the telescope. I had to convert that to a H5 format because the file is really big. It takes a lot of memory, so you have to do that separately. Then once you have that, you store the visibility information into a CSALT readable format. And I've just finished that. So now we're up to the orange stage, which is generating an MC-FOSS model and passing it into CSALT. And Christoph has been helping with that, the interface between CSALT and MC-FOSS. Then we're going to Fourier transform the MC-FOSS model into the UV plane with CSALT. And then finally, CSALT is going to be able to compute the residuals between the synthetic visibilities and the actual visibilities and compute a log likelihood for us that we can use it in our fits. And finally, stage 4 is putting it all together and my preliminary results so far. So I've been using the Bayesian inference library Bilby to run my MCMCs. So as it says here, it's very user-friendly and it will fulfill all your Bayesian dreams. So Bilby was developed here at Monash by Greg Ashton and a lot of other Osgrav people. So it's primarily used for gravitational wave astronomy, but you can also just use it to run MCMCs, which is quite handy because if I ever have any issues with it, I can just talk to people who sit in my office because a lot of them use it. So it's very nice. But a big advantage of Bilby is that you can very easily select any of those samplers. So I've been using MC, and we can probably expand out to a couple of other ones just to check what happens. And it's also very parallel. And it also makes nice corner plots for you. Nice in the sense that they look nice, not necessarily that your results look nice, because that hasn't been the case for me really yet. But here are some of my actual results comparing to the data. So this was back when I was using the SciPy optimize algorithm. So we didn't even include turbulence in the fit at all. And we were still able to get a really nice fit to the line profile. So even though in the Flighty paper, they found that they had to underestimate the central flux. Here we've dropped down the mass of the star to about 0.38 solar masses, and it looks pretty reasonable to me. Then we included turbulence, and we got the following results. So this is what it looks like on the line profiles. So still relatively good. The best line profile fit is a bit low in my opinion. But here I've done them up as actual channel maps. So this was for the line profile best fit. We got a stellar mass of about 0.35 solar masses and a turbulent velocity of 27 meters per second compared to 60 to 80 from the flight paper. So it dropped down a lot. And then for the data cube, the current best fit is about 0.33 solar masses and a turbulent velocity of 23 meters per second. So in both cases, it's dropped down by quite a bit in mass and turbulent velocity. I still wouldn't trust this completely because this was still with the dodgy uncertainties, but it's nice to see that in any case, the stellar mass always seems to be going down. And I probably should mention as well, other papers have used the higher stellar mass for DM tau. However, more recent investigations into the DM tau disk have found that having certain planet masses for gaps being carved in the disk, if you have the high turbulence values, is not compatible with the masses that they're getting for planets. So it could be interesting to explore if you had a lower turbulence value, if then the planet masses become realistic. So we've got some next steps for me to do. I need to figure out the uncertainty issue in the image plane fitting first, I think. And I would actually really like to run a fit with sea salt now that I've finally figured out how to get it working. Eventually, we would like to implement a multi-stage MCMC fit. So we would start off with our line profile fitting. If you get a good result with that, then you can iterate on to doing your image plane fitting. And then ultimately, if that's a good fit, then you would move on to visibility fits. And finally, since we've been focusing so heavily on DMTOW, and I'm writing up a letter on that, that's been my main focus at the moment, but eventually we would like to get this up and running, and then I would like to fit the parameters for all the XA disks on our newest high-resolution data sets. That's all I've got for you today. Thank you for listening, and I'm happy to take any questions.
Thanks, Caitlyn, for the wonderful talk. Does anyone have any questions?
I just have a really small question. When you're comparing your models and your observations on one of the last slides, was that like that difference thing? Was that also part of Bilby or?
No, that was just me calculating.
Okay.
Just like a subtraction difference there. Yeah, so Bilby is quite nice. The uncertainties are the big issue. So we're getting really small error bars still. And so that's kind of the whole reason why we distrust the 0.54 solar mass literature value for the stellar mass, because we checked where they got it from and that also has a really small error bar on it. So we'd like to sort out the whole error bar issue. But yeah, the Bilby
nice
plots.
plot.
Oh, thank you. Yeah.
What's the advantage to fitting the visibilities instead of the image plane?
Because then you're not contending with the calibrator's choice in their point spread function that they use to convert from visibilities to actual image plane. And also with sea salt, it actually has the covariance matrix for your MCMC, which is something that I haven't done when I did the first 2 rounds of fitting.
Do you still have to assume a point spread function to take your MC Foster, like your model result, into the image plane though?
I don't think so.
Okay.
Does anyone else have any questions?
What kind of price would you assume for your Bilby Bayesian inference?
Yeah, so what I've been using, so for mass and for turbulent velocity, I've assumed flat priors just because there doesn't seem to be much agreement anywhere. So they've got like pretty big ranges, flat priors. Some of the other parameters such as stellar inclination, flaring exponent of the disk, they've got actually quite well constrained stuff. So I've put like tight truncated Gaussians on those ones. Yeah.
Okay, thanks.
Most of them have like reasonable literature value. So I've tried to, the ones that have good uncertainties on them, I've stuck close. And for the ones that we don't know, just flat.
Let's thank Caitlyn again.